last year in 2019, a hydraulic fracture stage was completed every 40 seconds. That is a lot of fracturing. However, more than 1/3 of the wells completed underperformed expectations. And when surveyed, the operators actually gave reasons for the underperformance, 42% of which were modelable. So had the operator engaged in maybe rigorous modeling prior to completing those wells, they would have been able to avoid or at least mitigate the underperformance that they then realized. So when then ranking the importance of various improvements that would be available in the industry, improved modeling was ranked second after equipment reliability in what would be most impactful for unconventional operations. The objective of the ResFrac solution is to maximize economic returns. The knobs we have to do so in an unconventional completion are things like cluster and stage spacing, limited entry, landing zone sensitivity, well spacing, frac intensity like proppant and liquid loading, parent-child timing, spacing, and mitigating those interactions, thinking about repumping into the parent, refracking, and then also late life activities like IOR or EOR, or just a refrac. ResFrac feels that in order to do so robustly, we need to be able to simulate the entire life cycle of a well in a single model. So this is opposed to maybe some other solutions that have separate modeling softwares for separate phases in the life cycle of a well. In contrast, ResFrac, when you start a simulation, it starts with fracturing, proceeds directly to leak off, then closure, then production, and then any late life activities that you have, such as fracturing other wells in the model or refracking your initial well, all in a single model. And in doing so, it preserves the realism of the solution while also simplifying the workflows. And the final point here on the slide about ResFrac is that it is a broadly applicable solution. So it is a fully physics-based model, which means that it's not only applicable to unconventional tight shale, but also to conventional rocks, offshore, thermal, and geothermal environments. So what does it mean to have a solution that is fully coupled into a single coherent model? There are three major components in terms of the life cycle of these unconventional hydraulically fractured wells. So the first thing is hydraulic fracture propagation. So ResFrac is handling that in 3 dimensions, tracking all the proppant concentrations, all the fluid concentrations. So if you have multiple proppants and multiple injection fluids, the simulator will track each individually and you'll be able to see where each goes. Second, there's the reservoir flow component. So once you have created these fractures, how do fluids flow from the matrix rock into the fractures? And third, there is the geomechanical component, which is as this fluid flows from the reservoir into the fractures, how does the static conditions, or in this case, dynamic conditions of the rock change, namely poroelastic and thermoelastic stresses induced by production. ResFrac is doing all that in a coupled model. As a demonstration, I'm going to show a video of a simulation that is a parent-child simulation. The left-hand well in this image is the parent well, and the right-hand well is a child well. So the order of operations will be that to frac the parent well and produce for 3 years, then shut in the parent well, frac the offsetting child well, and then bring both wells back onto production. So in the upper left, we can see the injection rate and treating pressure for that first parent well. And then on the bottom right is the production profile. In the bright red is the parent well production, and the dark red is the child well production rate. In the upper right, I'm showing both the fracture geometries as well as proppant distribution. So the warmer color here is a higher proppant concentration. And then in the lower right, I'm showing pressure. So while fracturing, we'll see a very high pressure in the fractures as they propagate. That fracture pressure will then be drawn down when we go into production. And then you'll see pressure deplete in the matrix rock as well, surrounding those fractures. So again, this is a fully coupled solution, so it'll run end to end. The last thing I will mention before playing the video is that the axis of the wellbore has been stretched by 15 times, and that is to make each individual fracture more visible. So all we have done is take that image and stretch it such that we can differentiate individual fractures in the video. So I'm going to start the video. Here we see hydraulic fracture propagation in the parent. There's one stage. Here's a second stage that's propagating. We can see proppant ends up closer to the wellbore. Now as we deplete, pressure draws down in the fractures as well as the matrix. And then we are now fracturing the child well. And now depleting the child production, you can see pressure being drawn down along both wells. So one thing that we will notice is that the parent fractures were approximately symmetric in terms of balancing left and right of the wellbore, whereas the child fractures preferentially grew into and intersected the parent well fractures, causing an asymmetric distribution of fractures. So this could very easily then be the basis of a well spacing study as it related to parent-child wells. And as a consequence, you'll see that the child well underperforms the parent well. So depending on the economics of this production, it could be a suboptimal decision to have drilled these wells at this spacing. So to investigate why that happens, I've changed the angle, but same simulation, and looked at a few more properties. In this case, I have kept the same proppant distribution in the upper left and pressure distribution in the upper right. I have added then fracture conductivity, which is going to very closely correlate with the propped area. And then also the poroelastic stress change. So this is the stress change in the matrix due to depletion, and we'll actually see a reduction in stress, which is going to help us explain why we see asymmetric fracture propagation. On the fracture conductivity, I will note this is a static image that is taken in the middle of the child fracture, so you can see very high conductivity in that first stage of the child well. But if we look at the completed stages, you'll notice that there's an almost negligible conductivity in the unpropped regions, and then higher conductivity in the propped portions of the fracture. So ResFrac is modeling both the unpropped as well as propped portions of the fractures. So if we play the video again, we can see that initial parent frac, high conductivity, and then as those fractures close, the conductivity is going to remain in the propped portions. Now we are fracturing the child well, and we can see the asymmetric propagation. So if I come back in time to just before the child frac, what we'll notice in the bottom right, too far. What we'll notice in the bottom right is that the depletion that has occurred in the parent as it drained the reservoir has induced a stress change around the fractures on the order of 1,000 to 1,500 psi of reduction. So when we go to frac the child well, those fractures see a lower stress to the left-hand side of the screen. And as they want to go into an energy minimizing state, those fractures will preferentially propagate toward the parent well. This is the importance of a fully coupled model, is that we're handling all these phenomena in a single model and looking at how the different characteristics and processes interact with each other. This is the laundry list of questions that we often get of, can ResFrac do X, Y, or Z? Most normally, the answer is yes. So we include capabilities for things like black oil, modified black oil, or compositional fluid models. We're handling all phases of the hydraulic fracturing process, including fracture propagation, multi-phase flow, wellbore friction, depletion-induced geomechanics, etc., etc. This is a short video detailing the use and features of the ResFrac Job Manager. In this short video, we will cover navigating the interface, interacting with simulations and the hierarchy that they lay in, importing simulations, and creating a new simulation. ResFrac is organized in a hierarchy where you have projects, and within projects you have workflows. Within any workflow, individual simulations lie. If I come back to the project level, I can create a sandbox or workflow in which to create simulations. So I have created a new workflow called demonstration video. Generally, it's best for a field scale simulation to use the 3 stages, 8 clusters each, as a starting point. In doing so, it will create a simulation and bring up the builder. We will cover the full details of the builder in a future video. For this video, we're going to focus just on the manipulation of simulations within the Job Manager. In any page in the Job Manager, you can click the question mark, and it will bring up help content that will have a lot of the information that I give through the video, but in written form. A few features to go over. If you click the simulation name, you see a menu of options with which you can interact with that simulation. That same menu is available if you click the 3 dots or ellipses on the right-hand side. Also, if you click the chevron, it'll expand and give you more details. For instance, if I go up 1 level and choose a workflow that has more simulations that have already been run, I can click the expansion option and see more details about how long the simulation took and the time at which it ran to. If I have already run a simulation or a colleague has run simulations, I can also import simulations. There are 2 options for simulations. If I want to import a unrun or incomplete simulation, I can do so by importing the input and settings files directly. This is just 2 text files that are very easy to email back and forth. For instance, I can go in, and in my case, I'm just going to choose a simulation from another project within my ResFrac folder. So I can go to my June training, look at my default simulation, and what I'll do is I'll find my input file, and then my settings file, click import, and I will see that simulation. Now you'll notice it says not yet submitted because it is treating that as a new simulation. If I want to import a completed simulation, say that same simulation, I could come to import and choose import a simulation folder. I'll navigate back to that same simulation. Select the folder, press OK. And in this case, I have the choice to cut and paste or to copy, and I want to copy as I do not want to delete it from its original location. You'll see that it gives me an error because I already have a simulation in this workflow with the same name, and it'll automatically append copy 1, although I can also choose my own name. So I've chose to append import. I'll click import, and this time when it brings the simulation into my workflow, the full results will be available. So you'll see it says imported. And if I chose, I could visualize this simulation. If I want to add or remove multiple simulations at once, I recommend using the Windows Explorer to do so. So an easy way is if you click any simulation in your workflow and choose Open Simulation Folder in File Explorer. This will then open a Windows Explorer window with the exact location that this workflow sits on your computer. So if I come up one level, you can see here's my demonstration video workflow, and this simulation folder holds my 3 simulations that are also visible in my ResFrac interface. If I want to import multiple, let's say if I go back to that training project and go to June training, and I want to do, say, training sims 1, B, C, and E, I can copy those simulations, go back to my new project, and paste those folders in. Once successfully copied over, you'll see that those folders now reside in the Windows Explorer, but are not yet shown in the ResFrac interface. To update the interface, I come to the gear icon on the top ribbon and choose the option to refresh database. When I do this, you'll see it has identified new folders. I have individual files within those folders. If I exit the settings, you'll see that my new imported folders are now available. For deleting simulations that you no longer want, you can do so from the menu and choose Move to Trash. And then under Active Simulations, you can switch to Trash Simulations and see that simulation just deleted and choose to delete permanently. Alternatively, if you come back to the Windows Explorer, we can go and delete and update through the database like we did previously. So if I navigate back to my settings menu, click Refresh Database, it will update. I can choose to exit settings, and you'll see that my workflow has now updated with those simulations now removed. The last feature to show is additional options under the settings menu. In the settings menu, you'll notice that below the Refresh Database button that we've been using, there's also the current version of the software listed, as well as usage summary. If you're on an hourly license, you can check the usage summary to see how many of your licensed hours you have used. And if you are submitting a bug ticket or request for help, please note the version number when you do so. We may also ask you to click the Check for Updates button, which will ping the server and check for the most recent update. The first tab in the simulation builder is called Welcome. The rest of the tabs are laid out in a chronological order that is usually the order in which you're entering data into a simulation. In the Welcome tab, there's an overview video that gives an even briefer introduction to the simulation builder, an index which you can use to search for specific parameters. So if I type in proppant, it'll bring up a full list of all parameters that include the word proppant. And if I want to modify it, I can click Jump to Input, and it'll bring me exactly to that input parameter. And then the third tab within the Welcome screen is a list of updates. So every time we update the code, if you're interested in what new features or keywords were added, you can just look up the version number and then a full description of any changes that were made. The startup panel is where you define the physics of your simulation. You can see we have several options related to thermal calculations, fluid models, whether or not to include gas absorption or dual porosity.
and then whether to include poroelastic stress changes in the matrix. For any of these options, if you want more details or more details on any keyword in a ResFrac simulation, just click the question mark next to the input and a help panel will come up on the right-hand side that details the particulars of that keyword. One option that I do recommend checking here is rotate simulation mesh to align with stresses. What this will do is allow you to just put in the azimuth of SH max and your wellbore surveys as measured without having to worry about rotating the mesh to align for particular computational efficiencies. The static model and initial conditions panel is where we specify the geological and geomechanical inputs of our model. Typically, we lay that out in a layer cake model, and we can populate it from a log or existing geomodel profile. Again, at the top, we have options on how we input that data, and then we'll see a table with those properties populated by depth. To very easily import from a log, I can choose this properties versus depth wizard. At the top, I specify the number of parameters I'm going to import. For this example, I'll just choose 2, although it'd be typical to import 8 to 10 different parameters. And then a target layer thickness, I'll use 50 feet for now. I can also specify exact depths at which I want the wizard to separate my upscaling. But for this one, I'll let it just do it automatically. Now you can see I get an option menu to select which parameters I'm going to import. So if I look at my available parameters in my Excel, I have water saturation and SH min. So I will come back to the builder. I'll select water saturation as the first parameter to import and SH min as the second. Now I get a table that I can paste into. I will first click New Row, which gives me a writable area in which to paste my content. And I don't need to worry about resizing this table, as ResFrac will automatically resize the table to the size of your pasted region. So if I come back to Excel, I can select my depth, water saturation, and SH min data, copy, come back to the ResFrac builder, and paste those values in. Depending on the quantity of data being pasted, that may take 10 or 15 seconds to populate. Once pasted, I can press apply, and you'll see it has now populated, in this case, 56 layers in my layer cake model. Now there's a variety of other parameters that define the static model in our simulation. For this example, I'm going to keep those constant, but in a lot of instances, you would have detailed data on the depth profile of each of these parameters. So I will just put in 100 nanodarcies as my permeability in the X and Y directions, 0 in Z, and we'll cover curve sets in the next panel, but that is effectively my rel perm curves that I want to use for that layer. One trick to expedite the input of parameters in ResFrac is if you want to copy any parameters that are constant in a table, if you select those column headers and press Control D, it'll copy down that top value all the way through your table. So I'll do the same for initial porosity of 5%. And then also my pore pressure gradient, 0.75, and a Young's modulus of 4.5 million. Poisson's ratio of 0.25, and then copy these down. When I do so, you'll see that I used to have a red triangle error next to my geological facies input that has now disappeared. That red error indicates that something is wrong with your table and would cause an error if you tried to submit the simulation. So for instance, if I delete a pore pressure gradient value from my table, you'll see I get a little red X next to static model, which indicates that this will fail. So to remediate that, I'll copy down those values again, and you can see that turns back into a green check mark. If I want to see the values that I have imported in my table, I can press the 3 bars next to it, which will bring up a line plot of my imported properties. So the 2 properties that I imported were water saturation and SHMin. So SHMin is already pre-populated. I will come back and choose water saturation, press apply, and now you can see how my model has upscaled that log property profile that I imported from 7,500 to 9,000 feet. Finally, as I scroll down, you'll see that there's an input for direction of SH max. That's the azimuth of SH max. I will choose 75 degrees. And then the final input is a zero permeability cube. The zero permeability cube is a function within ResFrac to make sure that production is not double counted from reservoir regions that you anticipate being drained by a well not included in your model. If we were to look at this visually, if you had 3 wells in your model that were part of a larger 10-well pad, all at equal spacing, what we'd want to do is zero out the permeability at half a well spacing on either side of my outside wells. Typically, the way that we set this up is that this zero permeability region only activates just prior to a well being put on production. This allows fractures to grow within that region as they would during fracturing and to leak off. And then we only impose that zero permeability just prior to the wells being turned online. So I can do that by specifying an X, Y, and Z center of this cube, a rotation angle, and then a dimension in each direction. This bottom table gives me controls where I can start and stop at any arbitrary time. In this example, I only have 1 well, and I'm not going to input a zero permeability cube. The curve sets panel is where we input the relative permeability and pressure-dependent permeability parameters for each of our curve sets. Again, we saw in the static model that you can specify an arbitrary number of curve sets, and so theoretically you could have as many as 1 curve set for each layer in your geomodel. Typically, we would have 1 to 2 or maybe 3 curve sets. Maybe the most common implementation is to have 2 curve sets, 1 for your pay and 1 for your non-pay. If I open up a curve set, you'll see the default is to have Brooks Corey, but I have a variety of input methods that I can use. And here I would just specify the residual saturations of each of my phases, as well as a Corey exponent. For pressure-dependent permeability, this is what we use to account for the anticipated accelerated leak-off from multiple fracture strands propagating. This is a topic covered in our more in-depth training, but very briefly, core cross studies have observed far more fracture bands than hydraulically propped fractures. And so the philosophy is that we're going to model these hydraulically propped fractures and then constitutively account for the accelerated leak-off that would occur from the additional fracture bands. In this paper by Ratterman et al. In 2019, they show that the pressure depletion corresponds almost solely to these propped hydraulic fractures and not to the multiple fracture bands observed. Because fracture area and permeability are non-unique, we can account for this in a model by increasing permeability above SHMin. A very easy way to implement this is to use the pressure-dependent permeability wizard, set what you want the maximum permeability to be during injection, press apply, and then if you come and look at your pressure-dependent permeability table, the wizard will populate this table such that the initial increment in pressure is equivalent to that pressure differential between your initial pore pressure and your SHMin. And then above the SHMin pressure, you'll see that it multiplies permeability to enhance the leak off from those fractures. The wells and perforation panel is where we input the geometry of our wellbore, as well as the completion items like perforation spacing and perforation diameters, number of perforations, etc. You can see that because I created this from a template, there's an existing well in my model. For simplicity, I'm going to delete this well, and we will next import a well using a well survey. You can see there's a green wizard called Wellbore Survey Import. Here, I will give the well a name. Wells have to start with the word well, and then my practice is to append a number, although you may have an individual well name that you add there as well. We'll add an X, Y, and Z location for the wellhead, specify an inner diameter for the well, and then this last input is the centering position along the lateral. So we typically don't model the entire lateral, but instead model a subset of the well. And so we will include the center point along the well that we'd like to model. So for this case, I'll choose 9,000 feet. And then similar to the last wizard, we add one row such that we have a writable region in our table. Come back to our wellbore survey. Here you can see I've measured depth, inclination, and azimuth. I will copy those parameters over and then paste them into the wizard. Once those values are pasted, I will click apply. And now if I click the cube in the top ribbon of the builder, I will get an image of my wellbore. So now you can see that my well has been imported and the full trajectory thereof, and I've centered my matrix region around 9,000 feet. However, if I plot something like SHMin, which is what we populated, we'll see that the SHMin profile is not the same as that which I imported into my geologic table. The reason for that is that the depth of my wellbore survey and my log depth that I used are not reconciled. To fix this, I'll go back to the builder and choose Adjust Well Landing Depth Wizard. Here, I select my well, I select what landing zone I want it to be in. In this case, layer 31 is my pay zone. I'll choose yes, I want to adjust the matrix depth. And then within layer 31, I can specify a relative position, but I'll put it right in the center at 0.5, press apply. And now if I come back to my 3D image and press refresh, and once again plot SHMin, you'll see that my SHMin profile as designed is now located corresponding to my well survey. The final wizard to set up a well is the Well Stages Setup Wizard. In the Well Stages Setup Wizard, you enter a distance along the wellbore that you would like to model. For instance, if I have 3 stages of 150 feet each, and I want to model all 3, I would put in 450 feet for the measured distance in the model that I'd like to include, and then each of my stages is 150 feet. I can also choose to recenter the matrix if I want, but if I leave that blank, it will automatically center the matrix region around 0, 0 along these stages. Now, if I come and expand well 1, I can set up my perforations and clusters along the wellbore. If I have constant spacing, I can just use the inline method. Alternatively, you'll see at the top, I can specify clusters one at a time using exact coordinates. But for simplicity, I will choose just to use the inline method, wherein I specify the number of shots per cluster. So maybe I have 4 shots per cluster, each with a diameter of 0.32 inches, and I specify a coefficient of discharge. Then I'm able to specify the number of clusters in each of my stages. Typically, this number would be the same, and so I'll put 8 for all clusters. If I have an additional gap between my plug and my perforations, I can add that into what is called the toe gap input. For instance, you may have an additional gap of 20 feet at each of your stages to accommodate the plug, and so I could put in 20 feet in as an additional toe gap for each of my stages. Now, if I come back to my 3D image, once again press refresh, and then hide my matrix and show my perforations, I can zoom in and I can see my 3 stages. If I stretch my image, you can now see there's that additional gap in between each of my stages to accommodate my plug. The final input on the wells and perforations panel is that of an external fracture. An external fracture is a functionality added to ResFrac to account for stress shadowing from stages not included in your model. If you recall the convention of a ResFrac model, it's to label anything not included in the model and to toward of your first modeled stage as stage 0. So we can come back to our well number 1, expand, and scroll over to the stage number in the vertices table. If I scroll down to where I see stage 0, I'll highlight row 97, come across, and these are the XYZ vertices that define my wellbore. So I'll select one below stage 0 just to ensure that I have sufficient space. Copy those coordinates, scroll down to my external fracture table, add a new row, and paste in those coordinates. Now I have a couple options when inputting the data for my external fracture. I can specify a total volume or a net pressure. I often find it easier to put in a net pressure, so we'll choose 400 psi, and then the half length and half height that you would expect from a fracture. It will be centered around that vertex that we specified at the beginning of this table. So maybe my fracture has an entire length of 1,000 feet and a height of 500, so I can put in 500 and 250 as the half length and half height. Closure time and residual fraction allow me to degrade the effect of this 400 psi net pressure as that fracture leaks off. So I can say that the fracture closes over a period of 2 hours, and it eventually shrinks down to a quarter of that original net pressure. If you have subsequent operations or refracking or piled wells, you can use the additional options for secondary, tertiary activation times. In the meshing panel, we specify the geometry of each of the ResFrac meshes. To recall, ResFrac has 3 non-conforming meshes that are involved in the simulation. We have the wellbore, the matrix, and the fractures, all that are independent meshes and can arbitrarily cross each other at any angle. The first input on the meshing panel is that of the wellbore element length. A recommendation here is to make the wellbore element length just less than your cluster spacing. So if I had cluster spacing at 18 feet, maybe I'd choose a wellbore element length at 15 feet, and that ensures that the frictional pressure drop is calculated accurately for each of my perforation clusters. My next 2 inputs are for my fracture element length. This is one of the largest factors in a simulation runtime, and so I suggest starting at a larger element length, maybe 75 feet, and then I can choose an aspect ratio. If I choose an aspect ratio greater than 1, the length of my element will be 75 feet, and the height of my element is equal to my length divided by my aspect ratio. So if I chose an aspect ratio of 2, that means the height of each of my elements would be 37.5 feet. The center of the matrix region should be set automatically by the wizards in the wells and perforations panel. And then I can specify a number of elements in each of the directions as well as length. In the wells and perforations panel, I set up a well with 3 stages of 8 clusters each. The best practice is to have at least 1 matrix element in the X direction per perforation cluster. So in this case, that would be 24, and the length will have been set by the wizard in the wells and perforations panel. In the Y direction, we can use a very coarse mesh. The code is not very sensitive to the length of the elements in the Y direction. So 50 over 4,000 seems fine, although I might cut this region down. So I can choose to use uniform matrix elements. And if I'm expecting a fracture length of 1,000 to 1,500 feet, then maybe I will make my matrix region 1,800 feet long, just to make sure that I have enough room. And then finally, in the Z direction, we always recommend using this vertical mesh alignment tool. Here we specify the top of the matrix, the bottom of the matrix, and a target element length. So my inputted geology went from 7,500 to 9,000 feet, and I'll choose a target length of 50 feet. When I press apply, the code will automatically subdivide my meshing to correspond with the various layers that I input into my static model and initial conditions panel. In the fluid model options panel is where we specify the fluid parameters that we want of our reservoir fluid. Since we chose a black oil model in the startup panel, we will be given the options to build a black oil model in the fluid options panel. If instead you wanted to use a compositional model, you can go back to the startup panel at any time and choose compositional, and the layout of this panel will change accordingly. There are 2 dominant ways to populate this panel. One is if you have a black oil model already built, you can see that there is a table here where you specify the pressure, V sub O, RS, V sub G, oil viscosity, and gas viscosity as you would get in a black oil table just directly in the builder. Alternatively, if you don't have a pre-built black oil model, you can use the black oil wizard, and by specifying just a few parameters, the code will create a black oil model for you using the correlations in these SPE papers. So if we have a reservoir temperature of 190 degrees with an initial GOR of 1500, oil API of 32 degrees, and a gas-specific gravity of 0.75, press apply, and you can see it'll automatically create a black oil table for me. In the fracture options panel, there are really just two parameters that we'll pay attention to. One is the relative fracture toughness per square root fracture size. This is a scaling parameter that scales toughness as the fracture dimensions grow. For a more detailed discussion on this, please refer to our training videos on the website, but often a good value to start at is about 0.5, and you have the option to scale it either with a smaller or larger dimension. And then our practice is also to initialize the layer cake models with a small degree of random variability. I usually pick about 1%, and what this does is it just initializes the toughness in every single mesh element in my matrix with 1% variance. Other parameters that you might use on this tab are to limit the amount of production from unpropped fractures, which can allow the code to run much faster. So here, if you do like 1e to the minus 6, that will disallow production from any fracture aperture less than that amount. And then finally, if you refer to our training video, we do talk about this fracture swarms, something that has been observed in many core cross studies. And so we built the correlations directly into ResFrac. For instance, if you put in 3, the code will then automatically change the parameters to account for a situation where 3 hydraulic fractures actually propagate for each modeled hydraulic fracture. In the proppant panel, we specify the parameters of the proppants that we're including in our injection schedule. In this case, I'm going to have 2 proppants. So I will click New Row, and I'm going to use my wizard to populate the parameters of these proppants. To begin, I'll just copy down the values such that there is some value in this table. And then I have 2 proppants. I have 4070 and 100 mesh. So I will model my 4070 as a single proppant with a 55 mesh diameter, and then include 100 mesh as well. Now there is a proppant conductivity wizard where I can choose a proppant, so 55 mesh, which is my 4070. And then I can input a conductivity versus normal stress table to calculate my proppant parameters. So here's my closure stress and my proppant conductivity. I will paste that into my wizard table. And then a damage factor or multiplier, I'll choose 0.05. Now I will do the same for my 100 mesh. So I'll select 100 mesh from the table, again, come to where I have my values populated, paste those back into the wizard. I'll use that same conductivity multiplier and press apply. So now you can see in this table, the proppant pack compressibility, K0, and permeability compressibility has changed for each of my proppant types. And as a final step, I need to create mixtures. So I'm going to have 3 mixtures in my simulation. I have a 4070 proppant, and then 100 mesh proppant, and I define a mass fraction of each. So in 4070, I'd have 100% of my 55 mesh, and then in my 100 mesh, I would obviously have 100% of my 100 mesh sand. The final input on the proppants panel is the maximum immobilized proppant mass per area. This is to account for proppant that gets held up along the fracture surface as it's being transited down the fracture. A higher value here will result in more proppant being held up or trapped as it progresses along the fracture, and a smaller value will lead to less proppant being held up. This is a formation-dependent property and should be history matched to the data that you have available. In the Watersolutes panel is where we add the injection additives that we have to our fluid. You may have the N', K' parameters for your fluid, in which case you can use the proppants wizard, where you answer a variety of questions and you can bring in the parameter itself. Alternatively, if you don't have the values for your fluid, but you want to use a library, you can click No, you don't know the parameters, click Next, and then there are a variety of default fluids that have been included in the ResFrac simulation builder. For this case, I will choose slick water, click Apply, and now this friction reducer additive has been modified such that I have slick water-like parameters of my fluid. So now I have a water solute that's called friction reducer at a particular input quantity, and it has a downhole viscosity of 1.5 centipoise. You can get much more advanced with this with the import wizard, where you can actually import the exact profile and non-Newtonian parameters of a fluid. The final required panel to fill out is the well controls panel. In the well controls panel, we specify the actions that are done to our well or wells during a simulation. This is entered as a series of blocks. So I will first add a block. My first block will be defined as an injection sequence. And then in here, I choose what are my input units that I want to use in my table below. So I can input my proppant as mass per volume. I have choices on how to specify my injection rate. And then I define a maximum injection pressure for that entire sequence. Now, usually this is a history matching parameter, so I make that something arbitrarily large. And instead, I'm going to control on my injection rate and try to match what my actual pressures were. Then in my table, you can see I have a variety of input columns. The first one is duration. So if I come to my injection schedule, this is a series of ramps within a single stimulation stage. So I will select my stage time, come back, paste into my ResFrac model, and I'm going to choose that this is for stage 1, and I can copy down in my simulation. My fluid type is going to be that fluid mix number 1. For clarity, I can change the name of that fluid mix. So if I come back to Watersolutes, I can give this a name of slick water, and now when I come to well controls and open up my injection sequence, I will see that that is now populated as slick water, which just adds clarity when I'm reviewing my injection schedule and simulation deck. My next inputs are my injection rate, proppant type, and proppant amount. So I can, again, copy over my injection rate, my proppant type, and here starts one step down. So I will go to row 2, paste that in, and then finally I have my proppant concentration. So now that is my first stage that has been specified. And to specify the next 2 stages, I can copy and paste. So the first thing I'll do is I'll add 2 new rows. I'm going to add a shut-in between stages. So maybe that's 2 hours long. And I'm going to choose isolate wellbore, which is a shut-in. And then it doesn't matter what fluid type I pick because we're not injecting anything during this. The injection rate will be 0 and the proppant will be 0. Now what I can do is I'll select that entire table up above and paste it down below. And that is for stage 2. So I will change the stage number, copy, scroll down, and paste. And then I'll add 1 more new row. Once again, I will need to copy that entire table, scroll down, and once again, I will paste those values in. And I need to change the stage from 2 to 3, copy, scroll up, and paste. So now I have my 3 stages defined. I can use the plotting wizard again next to my input to confirm that I have input everything correctly. So here we can see my 3 stages being pumped, and I'm showing injection rate and proppant concentration. I can minimize that block by clicking the little arrow next to it, and then I'll add 2 more blocks. I'll add a shut-in sequence. So after I've pumped my job, I'm going to choose a shut-in. I have 2 options on shut-in. I can do a surface shut-in or an isolate wellbore. I'm going to choose isolate wellbore, which is computationally faster, and I'll change my units to days. Maybe my well is shut in for 3 days prior to being brought online. And again, we use an isolate wellbore here because that's going to speed up the calculation. The difference between surface shut-in and isolate wellbore has to do with whether or not you allow crossflow. So in an isolate wellbore control, the wellbore is taken out of the model, but the fractures still exist. So during a shut-in, this allows fractures to leak off, but it does not allow, same as what a surface shut-in allows, which is that a overpressured fracture can leak fluid back into the wellbore. That fluid can travel along the wellbore and leak out of a lower pressure fracture. Now, often the fracture pressure between fractures in a stage is fairly minimal, but it exists. And so in a numerical environment, this leads to lots of oscillation back and forth. That's why it's a reasonable approximation during leak off to remove the wellbore to avoid that cross flow and just have each fracture leak off independently. And now I want to specify the controls for my production sequence. To specify production controls, I can use the production sequence wizard. If I open up the wizard, I choose a well, a start time, and it's going to intelligently pick where to start the sequence. So if I put in 3 days, it'll know to start after that shut-in. The next input is averaging duration. So how many steps and what is the length of the duration that you would like each step to be. I'll choose 10 days, minimum bottom hole pressure default of 500, and a maximum rate. Remember to ratio this for the 3 stages that you're modeling, not for the entire lateral. And so in this case, maybe it's 150 barrels per day, and I'm going to default to bottom hole pressure. Then I'm given a table that I can fill out. So if I come to my input table, I have a tab called drawdown schedule. So my first column is days from sequence start, and then I will input a bottom hole pressure. When I click apply, you can see it has now inserted this number 3 production sequence. I can delete the second shut-in period, and if I go to the production sequence, you'll see it has populated as a series of 2-day increments and has averaged my pressure accordingly. If I want to view it, I can click the plotting function again. Here I can see that bottom hole pressure schedule being drawn down over about 130 days. At the bottom, there are several options. I recommend both interpolate bottom hole pressure and injection controls that will smooth out the simulator. And then this last one is also recommended and just makes a smoother simulation. That is the introduction to the ResFrac simulation builder. At this point, if I click validate, I will have a series of warnings that I can read through. These warnings will not cause a simulation failure, but instead are confirming that you intend to do what you have specified. For instance, when we set up fracture options, we specified both a relative fracture toughness as well as a fracture swarms. Generally, you would just input one or the other, although you can do both if you want to limit fracture size even more. So always read through the warnings prior to submitting a simulation to make sure it's accomplishing what you intended. Okay, and then you can always save and exit. And of course, the final step is just to run the simulation. So from the menu, click Run Simulation. You can choose a different simulator version if you want, but general recommendations to use the latest version of the simulator, and click Run. This will submit the simulation to the cloud server, and results will download progressively as the simulation runs. For updates, if you click the little arrow next to your simulation, you'll get updates as they come from the cloud server. Good luck, and let us know if you have any questions. This video serves as a brief introduction to the ResFrac visualization tool. To visualize a simulation that is currently running or has finished running, access the menu by clicking on the right-hand side from the Job Manager. From here, you can select Visualize Simulation Results. The visualization tool opens with 4 default panels, 1 line plot, and 3 3D viewers. The 3D viewers allow you to manipulate the image in a variety of ways to look at different properties. However, if you want to change the layout in terms of number of panels or type of panels, you can select from the expanded menu. To expand the menu, click the 3 dots in the lower right, and then if we click Panel Grid, we can reconfigure the visualization. So we could add additional visualization panels, or we can change the type. So if I want 2 line plots, I can just click Line Plot on the lower left. And then I can also decouple the camera angles. Because these 2 panels both say to camera group 1, when I rotate one image, the other will rotate with it. If I select camera group 2, I can then rotate the 2 panels independently. For instance, I can now rotate panel number 1, and panel number 2 stays the same. To modify the line plots, click the gear in the upper right. This gives a setup menu that allows you to select different trends, different number of axes, as well as the visual appeal of the chart. To begin, we can give it a name, like production chart. And then I'm going to remove the second axis. And from the first axis, I will plot the water production rate. I can then add back a second axis and include bottom hole pressure. And I could continue adding as many axes as I want, and I can assign them either to the left or right-hand side of the graph. We'll remain with 2. And from here, I can then rename my trends, and I can change the color as well as the type. So whether it's a solid line, dotted line, dashed line, as well as whether I want as a line or scatter plot. And then I can choose whether or not to include the legend. One recommendation is to make the text size larger if you plan to take a screenshot and put this in a presentation. Now I get a plot of my water rate and bottom hole pressure over time. I can zoom in to any portion of the plot by clicking and dragging, and I get a zoom window. And if I double right click, it will zoom graph out. If I want to compare the production data from one simulation to another, I can load an external data set and plot on the same graph. To do this, I navigate to the expanded menu and choose Manage Line Plot Datasets. Here, I can import a CSV dataset, and what you want to import is the file called SimTrack. So here is a SimTrack file. If you have field data, you can just format it in the same way as a SimTrack file. And now if I come to my gear icon, select, now you can see I have additional data sets. So now I could include the water production rate from my alternative or additional data set, as well as the bottom hole pressure. By default, the UI will default to those new trends to dashed lines so that we can distinguish. And to keep my color scale consistent, I'll choose orange for my bottom hole pressure on my imported data set. Now you can see both trends on there. I can easily come back and modify these. So instead of looking at water rate, I could come back and look at total water production for the 2 different simulations. And you'll see that it still defaults that external data to a dashed trend style. And now I can compare the 2 over time to see how they compare. There are also specialized plots. You access the specialized plot menu by pressing the little lightning bolt next to the gear icon. From here, I can select a variety of specialized plots, for instance, RTA plots. And once I set the parameters, it'll plot the RTA trends for whatever data I have available. So if I come back, you can see that I have both the simulation I'm looking at as well as my external data set. Again, I can give this a title, and to distinguish, I can change the color. And we can call this imported versus simulation. Add the legend, increase the font size, and now you can see that my title, RTA, with my 2 different trend lines from each of my data sets. In the 3D viewer, clicking and dragging will be a free manipulation where you can rotate the image in any manner. If you hold Control and click, you rotate around a single axis. If you hold Shift and click, it will translate the image as you drag your mouse. If you hold Control and Shift and click, it'll zoom in and out. In this way, you can easily position a 3D image to look at the exact angle that you would like to view. Additionally, it's often helpful to stretch the image. Here, you define a degree of stretch and a orientation in the horizontal plane in which you would like to stretch. The angle here defaults to the angle of your well, such that when you do a horizontal stretch, it will pull the fractures farther apart. I can also hide various aspects or show various aspects of the visualization. For instance, I could turn off the matrix. I could turn on perforations. And if you have faces in your model, you could turn on and off faces. I can also manipulate those toggles for individual visualization panes. For instance, if I want to look at pressure in the top panel in both matrix and fractures, I could select panel number 1 and turn on my matrix such that it only appears in panel number 1 but not panel 2. Additionally, if I want to take a slice, I can do so through the matrix slices menu. Here, if I select layers 1 through 5, it'll only show layers 1 through 5, so now I can see the pressure in both the matrix as well as my fractures. So I will zoom and set this to the angle that I would like. And then I may want to look at a fracture-only property in the lower right, such as fracture conductivity. Here I can define a log scale. And if we zoom in, we can see there's some variation in these preset rectangular fractures that I have in this simulation. I can change the ranges that I'm looking at by just clicking the min or max and typing in a new value. Once I have an image oriented the way that I like, I can save this as a layout. So I can save current layout and choose a name. This will allow me to open the same simulation with all my trend lines and images set to this same format, or open a similar simulation in the same orientation. For instance, if I come back to my job manager, I opened the 5 frac case, I can come and open the same 10 frac case using the layout that we just saved. Here you can see it takes in the same imported data so that I do not need to re-import my external data, and has loaded the image in the same orientation that I had previously with the same properties. So if I flip back to my 5 fracture case, I can very easily compare the two back and forth. Finally, if I want to see how this property changes through time, in the lower left, I can select different snapshots through the duration of the simulation. I can do so either by dragging this green bar and choosing a different snapshot through time, or I can type in the duration in the simulation that I'm looking for, such as 100 hours. I can also change the units if I'm looking in days, and I could look at 100 days, and it will adjust the image to the closest snapshot that it has available. The yellow dot on the line plots corresponds to the time at which the 3D image is representing. Finally, if I have run several similar simulations, I can use the multiplot function to expedite the creation of plots. For instance, I can click multiplot, batch create plots. I have the choice of what to include on my image. I then choose a template, and then I can choose the simulations for which I want to create a screenshot. As the screenshots are created, I get a toaster update in the upper right that tells me it's in the progress of making these screenshots. Once complete, the UI will open a Windows Explorer window with your new images created. So I can open up the images and very quickly compare 3 different simulations side to side. I can also very easily take all 3 data sets and bring onto the same line plot. Using the same multi-plot menu, I can choose compound line plot. I have to select a default layout, which we just created, and then I can choose the simulations that I would like to import to be able to select from in my line plot data set. I can also choose which simulation to show in the 3D viewer. Now, if I come to the expanded menu and look at my external data sets, you'll see that I have 3 external data sets, including the original one that I had when I defined this template, plus the 2 additional simulations and the base simulation that I selected from the job manager. From here, I'd want to go and edit the legend to make the descriptions more coherent and differentiate between my different cases, but I have saved myself a lot of time by using the multi-plot function.